All right, guys, we've got two examples here today, and hopefully maybe once we get through those, you'll have a little bit of time to maybe start your assignment. Just working with just strictly more examples of what we were talking about yesterday with the t-test. Remember, the t-test is going to be used when what situation has to occur, or what components do you have that decide the t-test over the z-test? Okay, so less than 30, so sample size less than 30, and what else? Okay, so the population standard deviation is not known. So if the population standard deviation is not known, what's a good substitute for it? Sample standard deviation. Okay, so as we do these, and we can and we will view these in alternative perspectives, because your homework's going to do this. Some of your homework questions say, what are the critical values? Okay, and then some of them ask, what is the p-value? And it kind of bounces back and forth. Some ask both, I think. So I think it's beneficial to, on these questions, do it using both techniques. So, first thing we always do is write our hypotheses. So we got our null hypothesis, and we've got our alternative hypothesis. Scenario says the physician claims that joggers' maximal volume oxygen uptake is greater than the average of all adults. Sample 15 joggers has a mean of 40.6 milliliters per kilogram and a standard deviation of 6 milliliters per kilogram. If the average of all adults is 36.7 milliliters per kilogram, is there enough evidence to support the physician's claim at 5%? All right, what is the null hypothesis? Or let's do it this way. Maybe this will be easier. Right there says that the physician claims that joggers' maximal volume uptake is greater. Okay? So greater, whenever you see the phrase greater, that is referring to which of these two hypotheses? Bottom one, or the alternative. So mu is going to be greater than. Okay? Says a sample 15 joggers has a mean of 40.6. Says if the average of all adults is 36.7. So this is kind of verbalized a little bit differently, because in all the other examples we've seen, like in this highlighted statement, that's where they would present one of, or the complete hypothesis, right? Here it's kind of broken up a little bit. We come down to this statement. If the average is 36.7, does it make sense to put 36.7 there? Okay. Then this would be, because it said greater, so this would be greater than 36.7. We've talked about this in the past. If you want to make these complete complements, it's not necessary, but you can do that, and now they are a direct complement of one another. Okay, but we must have at least the equality established in the null hypothesis. Which one's the claim? The alternative, good. States it right here. All right, so from that, and we know alpha is 0.05. So let's use this alpha to develop our critical regions, okay? Now, what tail is this? It's a right tail. So I'm going to just draw my area over here. Okay, so that's the rejection region, but we got to figure out what is the value. What is the value of alpha, the T of alpha, that provides it. So yesterday we talked about using Excel to do that. There is a command in Desmos, but off the top of my head, I can't remember what it is. You have to use, like, it's a series of composite commands that you have to use inside Desmos to get this. So it's kind of cumbersome, and we did it in Chapter 8 with confidence intervals, so I'll have to go back and see. I should have it in the notes somewhere. But Excel, I think, is the the easiest thing that's going to happen for you, or easiest thing to operate. You go T.INV, okay? It says returns the left-tailed inverse of the student T distribution. So we want our probability, which is going to be 0.05, okay, comma, degrees of freedom. So degrees of freedom is n minus 1. Well, how many? We have 15 joggers, right? So 15 joggers minus 1 would be 14. That's give me that number there. Okay, now that number, just think about this. Because the way Excel is structured, that is a left-tail cumulative probability of 5%. That's the t-score. That is the t-score that is actually attached to that area. Does that make sense? But since this is a symmetric curve, isn't that area there, if that's 5%, isn't this 5%? So if this was negative 1.76, this is positive 1.76. And I think that's the quickest, easiest way to determine that value. Okay? So that's your rejection region. Now, we need a test statistic. A lot of times, the test statistic, let me just double check this. We've talked about the notation that different authors use. I just want to make sure I use notation that's consistent with what MathXL is going to ask you. So, let's see here in a moment. All right, so Excel is actually calling, and I'm using sub-alpha because I think it makes most sense, because it's the t-value attached to that alpha. The text that I took the questions out from MathXL is going to call that T sub 0, and some text will call it T sub C. I actually like T sub C maybe best because C stands for critical value. But you might see that notation. They do a good job of saying, if you don't know what that is, they say find the critical value, and then they call it T sub 0. So there is a link there to that. Just be aware of that when you get to your homework. Yes, Blaze. All right, so to get the critical value, you're going to go to Excel and type in T.INV, and then it's your alpha, comma, degrees of freedom. Yes, you're not using Excel? Yeah, so if I go over there, I go 4. I believe I should probably type in the same thing, 0.05, comma, degrees of freedom. We'll get the same thing. So TI-83 is, you go second, vars, it takes you to the distribution, functions, and then go down to 4, which is inverse T. Yes? So you put what in? Okay, so there, if you put your test, so you're trying to find the p-value there. Because we haven't done the test statistic yet. So the only time I'm going to use inverse T is when I type in a probability under the curve, and it's going to spit back. So inverse T is, maybe write it here to the side. And it's the same for inverse norm. But inverse T, or T.INV for Excel, you type in area, it returns a standard deviation, essentially. It returns the 1.76 number. Okay. and that is your critical value, yes. If you use the norm.dist or t.dist, you're going to type in a standard deviation, and it's going to return an area. We'll get to so inverse t. Or that's what your question is. There's two things going on here. There's inverse t because we need to find critical values, and what we're going to do then is compare that critical value with the t-score from our data. So I just write t sub d here. We're going to go and run through this thing in a moment. Once I have that, and I want to compare that value directly to a critical value, those are the things comparing. I'm essentially comparing standard deviations. If I want to take and just compare the alpha 0.05 to something, then I have to run through that t-score of my data, get that standard deviation back, and then convert that into an area, and then compare that area to alpha. That critical value is from alpha. This blue value right here, that came from knowing I typed in that right there into Excel, and it tells me then in a curve that has 14 degrees of freedom, if alpha is 5%, if I want that area to be 5%, then 1.76 is that t-value that creates that upper 5%. So if we run through this z-score here, t-score, x bar is the sample mean. So if we look at that, it's going to be the 40.6. Yeah, sub d, so for data. And you can, and that's the thing, as I work on these guys, I might use different notation because ultimately the end result, the end conclusion we want is reject or fail to reject, right? So all the things that we do on the way there, I like to use notation that makes sense to me so I can organize my work, okay? Because obviously you guys know me, when I'm working, things are all over the place, right? Pretty bad organizing and being linear with my work. But if I label things, because I know that sometimes my organization is haphazard, labeling things to where they make sense to me allows me to search through my mess and find those values that I need. So x bar was 40.6 minus mu. What's mu? Good, 36.7. Sample standard deviation, 6. And then square root of n, so 15. So we evaluate that. So we go 40.6, 36.7. And it gives us 2.517. 2.517. So now when I compare that 2.517, that's the test statistic. And that's what we're going to use to compare to our critical value. The test statistic is going to fall over here somewhere, right? Maybe right there. Quite a bit further to the right of 1.76. So, that being said, what does that force us to do to our null hypothesis? We reject it, okay? So we're going to reject the null hypothesis, and then we can argue that there is evidence to support our claim that the average is greater than 36.7, okay? So the oxygen uptake of joggers is greater than the average of all adults. Okay. Now, and that's perfectly fine. If we're on a handwritten test, quiz, whatever it may be, and this question's presented, and it does not tell you the technique that I want you to use, you have full freedom to use anything you want, right? Do you like that technique? I like critical value technique. I think it just makes sense more for me. Okay, you can go ahead and use that, but we should also be able to gain the same exact result by comparing areas. Okay, now think about this, because we really already have all the work. If we look at this value right here of 1.76, okay, that means this area here, okay, that's the area of alpha, which is 0.05, okay, and we just found that, I don't know the number it was, 2.517, okay, that's going to be, that area in blue right there is my p-value. Okay. Now, regardless of what that p-value is, and we'll come up with it in a moment, but when I compare my p-value, right now that area is less than the alpha area, is it not? So what did we do? We rejected in this situation with critical values. So when I use p-values and I see this relationship that the p-value is less than the alpha area, or the alpha value, then I still have to make the same rejection that I did with critical values, right? So that's kind of how, if you remember 2 or 3 days ago when we were talking about z distributions and the p-value attached to those, we had 2 consequences. If our p-value area was less than alpha, we rejected, okay? If the p-value area was greater than alpha, you failed to reject. Does that make sense? And it ultimately comes back to the idea that if my p-value area is less than alpha, that means my test statistic is further to the right, in this case, because it's a right-tailed test, than my critical value. Okay, so if p-value is less than alpha, that basically means your test statistic is falling in the critical region, okay, or the rejection region. Now, why they use p-values is because it eliminates us having to find this 1.76. Okay, so we know alpha is 5%, 0.05. We know that the t statistic from our data was 2.517. Okay, what we want to do is find the area attached to this t-score. And the way we're going to do that, because now we're typing in a t-score and it's going to spit back the area, that command is the t.dist command. Okay? And you can see here it says it returns the left-tailed student t distribution, which is ultimately returning an area. And that's going to ask you, well, what is the x value that you want? Okay, now here's how I'm going to do this, because it's going to return a left tail. If this is 2.517, if that's that t-score to produce this area here, is there a t-score over here that is going to produce the exact same area? Okay, what would be the value of that t-score? Negative 2.517. So that's usually the way I will type it in. So we go negative 2.517. You see it says degree of freedom. Okay, so we want 14. And it says cumulative So you'll type in true. And it gives me that area there. So that's my p-value. Okay, so p-value 0.012. Okay. Now the command on Excel, the way I typed it in, was actually finding that area right there of being 0.012. But we know the symmetry exists, right? If I don't use, and this is just something to think about, and this is, hopefully you would realize that you've done something maybe not wrong, but you got more to do if you type this in. If I go t.dist and then type in x to be 2.517, degrees of freedom 14, cumulative true, I get a pretty large number there, correct? Okay. And when you get a very, very large number like this, remember comparing to alpha, where alpha is 1%, 5%, 10%. Here I get 98%. Chances are that you have the complement of what we're looking for here. Because the way I type that in, because it's a left cumulative command, it's finding all the area under the curve up to this blue stuff. Okay? Well, if I want the blue stuff, then I got to take that number and remove it from 1. So you'll 1 minus that number. And you see there, you get the same 0.0123 that the initial way we did it returned. So p-value 0.012, alpha value 0.05. So what I always like to do is, I'm always going, when I make my comparison, to make the rejection or non-rejection, always put the p-value first. Okay? So 0.012, and then I compare that to 0.05, is 1% less than 5%. So I can keep that inequality that direction, and that tells me to reject the null hypothesis, just like the critical values told me to reject the null hypothesis. Yes, yes. And that's what's going to happen in your, and that's what I was saying at the beginning, when the question is just presented to you and you don't have predefined boxes like on Math Excel to type in a critical value, or predefined box to type in a p-value or something like that. It is your freedom to choose either technique. Okay. In the event that your main goal is to just make a decision on the null hypothesis. However, we said this several times throughout the week. Remember, when we're doing these problems, not only are we trying to be able to learn how to do them when we put ourselves in that situation as the researcher, but we also want to be able to learn the math so that I can become an intelligent observer, an informed audience. So when I'm reading somebody else's work, I actually know what I'm reading. Does that make sense? And most times when you're reading somebody else's statistical work, they're reporting p-values instead of the t or the critical values. So there's different, I don't know, like arenas in which you might have to use critical values or understand critical values versus p-values or vice versa. Does that help? Does it make sense? The one thing I think maybe, and I get confused with it as well because we don't use Excel and those things all that often, but the command t.dist, okay, or norm.dist, okay, those two commands, okay, will return, because that's what we used right here, okay, and the return, these values here are areas, okay, so those are going to return areas, and the input is ultimately a standard deviation, because that's what this curve is, right? That's saying 0, and basically we're saying that our sample data was 2.517 standard deviations away from the mean of 0. Okay. The t.inv in, is it norm.inv or is it inv.norm? Norm. Okay. Those return, so I'll write this way, critical values, which your critical values are ultimately the standard deviation that we're looking for, that 2.517. And then you can parallel that to what Desmos offers as well in their commands. So let me see. I'll have to search back to, I think, chapter 8 real quick. Yes. I don't know yet. What would you want it on? We can do it on Math Excel, but I'm just, because you're not always, I mean, when you're putting yourself in the role of a researcher or role of a observer, you're not always going to be using Math Excel, right? And that's, I mean, I guess that may have to talk about the perspective of why we're learning this stuff or why we're in the class, but not necessarily in the class. Like, the goal is not just to, and I know it is a goal, but not just to get through the homework or to get through tests and quizzes and that stuff. It's to obtain knowledge that can last with me beyond the class, that I can actually then utilize in a purposeful way. Quit shaking your head no. You. And this is what I was talking about, is it's a pain in the butt to get Desmos to use the inverse commands, because you have to type in inverse CDF, spell it right, and then you type in T distribution, and then you have to know what goes in the T distribution, and I believe what is going to go in there is your, well, actually, let me see this, T dist, degrees of freedom, that's it. Okay, so I'm typing my degrees of freedom. Should be something else I need from that. 2.517. I'll figure it out. But I guess it's a good situation. Like, this is not convenient. Excel is built to be convenient. So TIA3 is built to be convenient. I would use those things in place of Desmos. There we go. So you got to type in, so you go inverse CDF, T distribution with your degrees of freedom, comma, then your alpha, and you see there that would have given you the 1.76 that we were getting right here. Okay, so it's up to you, but use the tool that I think is most convenient.